In this lecture, I'm going to give you an outline for what you will learn in this course, in what order you will learn these topics in, and most importantly, why it's in this order. On top of that, I'm going to tell you where this course will lead you and what exactly I'm setting you up to do, specifically deep reinforcement learning, which is the application of deep learning to reinforcement learning. But more on that later. Let's start with the first topic, the multi-armed bandit. The multi-armed bandit is a classic problem. It's actually very applicable in the real world. As you'll see, pretty much every online business can make use of bandit algorithms. The multi-armed bandit can be looked at from many different perspectives, and in this course, which is about reinforcement learning, that's merely one of them. You can also think of multi-armed bandits in terms of recommender systems and A/B testing. So if you want to step away from reinforcement learning, which is pretty much an academic subject, and look at it from an A/B testing or recommenders point of view, that might be helpful. It should be pretty obvious to most of you that A/B testing is something businesses do. It's pretty much the most business-like machine learning thing that you can do. So if you're ever thinking, why is there so much math? It's because you're losing sight of the big picture. Any business that recommends or displays products, such as Netflix, Facebook, Instagram, Amazon, Google, Walmart, Bank of America, McDonald's, Target, the New York Times, BuzzFeed, Apple, Coca-Cola, Nike, Adidas, Kellogg, Ralph Lauren, Nintendo, or Forever 21. All these companies are interested in A/B testing and recommendation systems, and therefore a subset of reinforcement learning. I hope I annoyed you a little bit by making that list just a little bit too long. That was the idea. You want to understand that basically, everybody can make use of this technology. After learning about the bandit problem in depth, we will then transition to full reinforcement learning. This all starts with a model. Without a model, we can't do much else. The model encodes assumptions and relationships between different components of a system. For example, pretend you're a school teacher. You might say, I model my students' exam grades as a normal distribution. But another teacher might take a more sophisticated approach. They might say, I model my students' exam grades as a linear function depending on how many hours they studied. Of course, all models are necessarily simplifications of the real world. For example, the model of a reinforcement learning system will be an MDP, a Markov decision process. Using this framework allows us to answer questions like, what will be the result of my agent performing some action in the environment? And what is the value of that action? Or in other words, how much is that action worth? To do this, we're going to consider three main approaches. Without going into detail, these are number 1, dynamic programming, number 2, Monte Carlo methods, and number 3, temporal difference learning. Temporal difference learning includes the popular Q-learning algorithm, so if you came here to learn that, it will fall into category number 3. What you will learn is that these three main approaches make fewer and fewer assumptions as we go from number 1 to number 3. So dynamic programming will be very restrictive, whereas Monte Carlo will be less restrictive, and temporal difference learning will be the least restrictive. At the same time, as you advance, these techniques will become more brittle and less robust. So with great power comes great caveats. We will test all of these algorithms in what is known as the grid world environment. The grid world environment is a very basic game with a very small number of states and actions, so that everything is enumerable and you can see it right in front of you. Being able to visualize reinforcement learning is very useful at this point, since in more complex environments, things will be much more abstract. Once you've learned about the three main approaches to reinforcement learning, we will start to incorporate supervised machine learning into our algorithms. More specifically, we will use models that you might be more familiar with from the land of supervised learning and incorporate them into reinforcement learning. The main requirement is that these models be differentiable. So for example, linear regression and neural networks would be a good choice. The use of neural networks would be considered deep reinforcement learning, which is a topic that is outside the scope of this course. If you want to know why, you can wait until a later lecture, or you can ask me about it on the Q&A. However, what you can see is that including neural networks in this process is a pretty obvious next step. And so basically you can think of everything we learn as what are the prerequisites to get you to the point where you can understand every aspect of deep reinforcement learning. Finally, in order to apply everything we learn in this course, we are going to build a reinforcement learning stock trading bot. This is the culmination of everything you learned in the course so far, applied to something it seems like a lot of students are interested in. We will use Q-learning, which is the final learning approach we will learn about, combined with function approximation methods from supervised learning. So if you think about each topic you learn in this course as a step-by-step process, where one topic leads to the next, which leads to the next, this is the final thing, where you can take everything you've learned and apply it to something more real world. So to summarize, this is the outline for this course. The first section focuses on several algorithms for the multi-arm bandit problem, which not only can be considered a topic of reinforcement learning, but also recommender systems and A/B testing as well. As you'll see, it's one of the most easy to apply algorithms in the real world. Next, we'll look at a kind of toy reinforcement learning problem, where you will learn how to implement a tic-tac-toe agent. As mentioned, this won't be real reinforcement learning just yet. This is just to help you get used to some of the main ideas and apply them right away. Next, we will start talking about real reinforcement learning, and that will be the subject for the rest of the course. This is where you will learn about MDPs, dynamic programming, Monte Carlo methods, and temporal difference learning. This is the heart of the course. Lastly, we will apply reinforcement learning to a real dataset, namely to build a stock trading bot. Earlier in the course, we only looked at the grid world environment, since it's visualizable and easily interpretable, and therefore very intuitive. Building a stock trading bot sounds more practical, but in fact it's much more abstract in many ways. So everything you learn will culminate in this one final project, which will apply all the concepts you absorbed earlier in the course.